Okay, Coulter, I'm going to show you this example I created for you. In a lot of ways, there's kind of overkill in this example, but it's not some of the things you won't need, but maybe you commented on in your email. So I went ahead and did them, and you can use them for other stuff where it might be needed sometime. Okay, so we got our main routine, and then I've got a subroutine here, and I'm calling it fuse. And we're passing in some data. We've got what I'm calling HMI bit, and I'm not actually creating the Modbus attachment to these things. But I've got, you can see this, I've got HMI bit, that'll be coming in from your HMI. You've got the input bit, that's going to be the switch that could otherwise turn it on. You're going to have a fast fuse, that's going to be the value, the analog value. The slow fuse, that'll be its analog value, basically the limit. You've got the slow time. You have the actual analog input, and you've got the actual analog output you'll be tying to. And I'll show you in the main program how we tie to them in a minute. But a couple of important things here are we're making the HMI bit and the analog output pass by reference because we want this subroutine to be able to change the value in the main routine. And the only way you can do that is by selecting this pass by reference. Okay, now I'll show you our main routine, and you'll see it's all in a. Actually, since this is a subroutine, I should always be exiting this. So let me change this logic just a little bit. If it was the main routine, I'd want it all in a big loop, but this is not the main routine. I need to be exiting. You always want to exit subroutines as quickly as you can so that it can go about its other tasks. Okay. So the priority item here is checking to see if the analog input is greater than or equal to the fast fuse value. If that's ever true, then we're going to put our state machine, which we haven't started discussing yet, we're going to put it to state 0. And we're going to turn the input bit. We're going to turn it off. I don't actually think we want input bit there. We want the HMI bit. We're going to turn the HMI bit off. And let me make sure I have that. Yeah. We're turning the HMI bit off, and we're going to turn the output bit off. Okay. Assuming, and you see, if that's the case, then it's going to go through this pattern right here. And it's going to end up returning. It does one other thing. We do a little bit of record keeping here. You were asking about doing things based on a transition. Maybe it had gone from, you had an input that was off and now is on. You're wanting that rising edge signal. In order to do that, at the end of each scan, we need to go ahead and record what the value is so that next time we're wanting to check the values, we have something to compare it against. So we'll have this, we're copying the input bit to something I call last input bit, and the HMI bit to something called last HMI bit. And you'll see in the state equals 0 that I'm going to ask a question, a series of questions that tells if we've encountered a rising edge. So we're asking, is the last scan input bit off? If so, is the input bit now on? So has it gone from off to on? If so, we're going to do something. And we also ask this other question, was the last scan HMI bit off? If so, is it currently supposed to say on? Is it on? If so, do that same thing. And that thing is we're going to be turning on the output bit. You see that's the second line here. We're also going to be advancing the state. And we're going to be resetting the fuse time, which if you copy 0 into a timer, that's the same thing as a reset. So you asked about this. Your solution didn't actually involve this, and I agree. I don't think you need it, but you did ask about it. So I wanted to, in case a future task really does require knowing when it's transitioned, you'll kind of know how to do that. Okay, so we've advanced the state. In this state, you can watch our video tutorial on state machines, but it lets you just kind of focus on one task at a time, and it kind of helps break apart your code. So we were at state equals 0. Your value, when you enter the subroutine the first time, all your values will be equal to 0. All the local registers will be equal to 0. So we took advantage of that by asking was it equal to 0 the first time. And you see if these cases are true, if it either followed this path or followed this path, then it's going to be changing the state equals 1. And you see, again, we're going to be exiting the subroutine. But next time we come here, next time we enter the subroutine, now, assuming the analog value isn't greater than the fast fuse, then the state is going to be equal to 1, and it'll jump down here. And in the state equals 1, what we're doing is we're just checking to see if the slow fuse has been met. If it is, we start a timer. If it isn't, we reset the timer. And then we're hanging out. We're checking if is a timer greater than your fuse time that you set. Again, I got a mistake here. I'm wanting to ask if my I'm going to have something called my timer. Defined as a timer. And we'll be asking, is my timer greater than the fuse time that you set? The fuse time is what you're setting on your HMI. I got to change it here too. Okay, my timer. Okay. So if the slow fuse was met and over a certain time has elapsed, then what we're going to do is we're going to be setting us back to state where we're waiting for that input bit to happen again, and we're going to turn off the outputs, and we're going to turn off the your HMI bit. I've got a few mistakes scattered around. Glad I'm talking through these. Okay, so I think at that point you're good. And again, all of these conditions are going to be copying the current state into what we're calling the last state of these, the last value of them, so that they'll be ready the next time. Okay, so that's our subroutine. I'll save that. The main routine, you'll see, well, if you take a look at the structure, we've got our main routine and we've got our subroutine. And right here to the right of this, we've got our number of instances we're declaring. And what that does is it creates a separate object, a separate data object for however many you want. So that allows the internal data to the subroutine to be maintained even when you jump out of the subroutine. It's got its own memory, so for instance, the last scan values for each particular instance of this subroutine, it's going to be maintained. So you want to declare as many as you need, and then you'll see each call of the subroutine, I've got an object number, so I'm doing 1 here, I'm doing 2 here, I'm doing object number 3 here. I think in your case you're wanting to use 12, but I just did 3 for simplicity. And then I've got I'm passing in my particular values that are important, that are unique, as well as some of them that are universal to all of the instances. So I'm going to pause this for just a second. Okay, so you'll see that we've got some of these values that are going to be the same on each of the subroutines. You've got the fast fuse value with the slow fuse value, the slow time value. Those are going to be, in each of them, they're going to be the same thing. But then you've got some data that's unique to each instance. We're passing in the particular HMI bit, which I haven't tied to the Modbus addresses, but you could obviously, tie those in. And then I'm putting a particular input bit into what I'm calling input bit in the subroutine, and I've got the particular analog I'm tying in and the particular digital output. So that's what lets you reuse your subroutines for many different similar systems. So you're controlling 12 things, but you only have to write the subroutine once. So I think that should get you started, but just let me know if you have any questions.